Okay, so good evening to all of you. My name is Abhinav Sharma. I am a PMR fellow at the Department of Design in IIT Kanpur. Welcome you all to this second session of the NPTEL course on Engineering Meteorology, which is being taken by Professor Ramkumar at IIT Kanpur. So, in the last class, we have discussed about the differences between the accuracy and precision. We also dealt with what are absolute values, what are true values, what are measured values, how is the error calculated, how do we differentiate between absolute error and relative error and percentage error, what are different types of instruments. So we did all this in the last class. Today, to begin with, I would first of all ask you if you have some doubts from your previous sessions, the lectures that have been taken by Professor Ramkumar, or any other doubt that you think needs to be solved at this stage. You can ask your questions and then we shall begin accordingly. Okay, so if we don't have any question, let me begin with uh, what exactly is the definition of resolution for an instrument, for a measuring system, for a measuring device. Let me just start from this fact that how do we differentiate between resolution and the least count, and what exactly does the resolution means, and in what type of instruments do we need resolution, and what exactly is the need to understand what resolution is. So I will share my screen from here on, and if you have any questions you can just raise your hands or you can put up your questions directly into the chat box and we can take those questions later on. Okay, so you can see the screen right now. Can someone confirm if you can see the screen?
Yes, sir. Yes, sir.
Okay, okay. So welcome to this second session on engineering meteorology, and let us begin our discussion today with what exactly is resolution. So this word comes from the root word called as resolve. So from resolve, we have made a word called as resolution. Now, when you see one more word, I should take it side by side, that is called as least count. Many a times when you go through the, okay, sorry, yeah, so here, we were here. So many a times when we go through these two definitions of least count and resolution, we see they are kind of synonymous and they are confusing. Let us see first what resolution is and what least count is. So, if I say for least count, the minimum value that can be measured that can be measured by the instrument. Now, what does that means? Or before coming to it, let's see what resolution is. So if I say what is resolution, we can say the minimum incremental value measured using a device or an instrument or a measuring system. Now, uh, what basically is the difference between these two, and why is this word incremental important here? Incremental value, what does this mean? So, to see this, let us take an example of a galvanometer. And if we consider this to be, say, not a galvanometer, any deflection type of instrument, and we have a pointer here and we have lot of scale here. Okay, so this is the kind of instrument that we are using right now. This can be the speedometer that you see on your cars. This can be a galvanometer that can read currents. It can be any instrument. For general purpose, we are reading it. So we want to clarify on the fact that what is the difference between the least count of a device and the resolution of a device. Are they the same thing? So as you can see on this section, there are multiple scales here. There are multiple scales here, subdivisions of subdivisions of the main scale, and we have a full range of movement from here to here. Now, when I say least count, I say the minimum value that can be measured by the instrument. Now, if this particular scale here, it ranges from, say, 0 to 5, then 5 to 10, 10 to 15, 15 to 20, 20 to 25, and 25 to 30. Okay, so if this is the scale range and the sub ranges are then 1, 2, 3, 4, 6, 7, 8, 9, 10, after 10, 11, 12, 13, 14, 16, 17, 18, 19, and so on and so forth. So if my pointer starts to give me a value and the minimum value that it reads is, say, this, and after this, when it starts to move, the first value that it gives is 1 or 2 or 3, whatever it starts to give. The minimum value that we read at this point of time is called as the least count of the device. Okay, now coming to the resolution of the device. Fine. This is important to understand here because when we will talk about the least count, we will say that uh, it is calibrated in terms of the errors. So we will have to see that what is the least count error from here on. Now, if we talk about after having understood what is the least count value, the minimum value that the device can read, now we say that what is the resolution, and in the definition of resolution we have written a very important word called as the incremental value. Now, what does that incremental value means? Say we are reading the speed of a car by this instrument, this measuring device, and my device can give a deflection from, say, from this zero position to till here, that amounts to be 3 units. Fine, then this becomes my resolution. Now, how will we talk about resolution of this? That my resolution is 3 units, and this means that if there is any deflection between 0 to 3, it can only give me values either 0 or 3. It will not give me values 1 and 2. So if a value is near to 0, it would approximate it to be 0. And if a value is close to 3, it would approximate it to 3. It would not give me values such as 1 and 2. So this is the resolution of my device. That the minimum value it reads as the increment. Now, if there is a value that corresponds to a value lesser than the resolution of the device, it will always give an error, and it will always show you the value that minimum it can resolve up to. From this word resolve, we make the word resolution of the device. Now, let us see one more example to understand this. This was an analog kind of a device, a meter, analog meter. Now, if we go through, and we have not discussed analog devices and digital devices as of now, but let us first see this example, and then later we will go on to the types of instruments. Now, say if this is my digital multimeter and there are so many controls over here, and if I want to check my values, whatever current and voltages are here are depicted here. Now, if this is the resolution and I have two decimal places after the points, and this is a very good example to understand the concepts of resolution. Now see, if my value of voltage is, to be very precise, 10.2567 volts, what would be the result that this kind of a device would give? So see, to better understand this, we have some values here which are not a problem for us in any of the cases. So anything above decimal would not create a problem. Now, if this has a resolution of two bits after the decimal places, or two digits after the decimal places, the maximum or the minimum it can read is, say, zero point 0.01, 0.02, and 0.03 here on. So the difference becomes as 0.01. Now this is the least value it can display on the board here. Now, if my value to be displayed is 2567, how would it show on my meter over here? Because it has a limitation that it can show only up to 0.01, as an increment of 0.01. So there are two things. There are limitation of the digital display keys here, and also the resolution is minimum 0.01, as we have taken here for the example. So it will automatically approximate this value and it will show it up as 10.26. This value would go for approximation, and these two values it will approximate to the next higher digit that is available for display. So 10.2567, my device would read as 10.26. This happens when the resolution is of 0.01 in these cases. Now say if my resolution was 0.05, or say, to be very true, 0.06, to understand what is the difference between these values. Now, if 0.06 is the minimum resolution it gives us, or the minimum value that increment it can read, so after 10.06, it would read something as 10.12, and then it would read as 10.18, and then it would go for 10.24, and after reading 10.24 it can read the value called as 10.30. So what happens to this value 2.567? This is a very interesting case wherein we should know the limitation of our display devices. We should know the limitation of our instrumentation systems. The minimum incremental value that it can read here becomes 0.06. Now, if it is 0.06, it can read 10.24 and it cannot go beyond 10.24 to 10.25. It would read as 10.30. Is this clear to everyone? Do we have questions on this?
No, sir, got it.
Okay. Rest others who are here, if you have some questions, can you please ask?
No, sir.
Okay. Okay, so this is a important concept to understand here for the future, wherein you will need to solve numericals and problems and even design systems that have to measure the real-time value. See, reading instrumentation and understanding instrumentation has two parallel concepts. One is the theoretical concepts, and other is the developmental thing wherein you actually need to put in your devices that you design. So now, if these concepts are clear, it would be helpful for you to understand how does the instrumentation systems or the measurement systems actually work in real time. Now these values can be anything. These values can be the voltage reading in a power plant, voltage in a power plant, voltage and current, I'm assuming to be the same counterparts. Then it can be the temperature. The temperature can also be one of the things in a furnace, or you find the furnaces in a lot of industries. It is the power plants, it is the blast furnaces in the glass industry. Then there are furnaces in the manufacturing sector. So there are a lot of industries wherein these kinds of systems are needed to measure the voltage, temperature, pressure, and different other values and parameters that we discussed in the last class. So you have to be very precise in understanding the fact that there is a minimum limitation to every device. You cannot make it absolutely perfect. And this is where the choice of the designer comes at the play. How does the choice of the designer works here? Exactly in the example that we understood, that our value to be read was 10.2567, and the meter that we choose could read only in the resolution of 0.06, so it would not give us values such as 0.2567. Now, if it is a case wherein there can be two cases. One is where you can accept the tolerances, and the other can be wherein you don't accept any of your tolerance. Now, how do you decide that you can accept the tolerance or you cannot accept the tolerance? Depends on the kind of work that you are doing. Say if it is an agricultural sensor that you are trying to make, and we would eventually move on to control systems from here on to understand. So reading sensors is something important. Now if there is an agricultural application wherein you want to measure the moisture of the soil, and it is not very redundant example to understand the practicality of the systems that we deal. So if you have to read the moisture of your soil, and you can tolerate the values that differentiate between the soil not being too wet and being sufficiently wet, then you can accept the tolerances like this over here. But say if you are working in a nuclear plant wherein the pressure ranges cannot exceed zero point zero 0.01 units, in that condition these kind of systems would fail. So we will have to choose our systems, we will have to design our systems that adhere to the resolution that is needed by our system. Is this understood to everyone? Where do we actually apply the concepts, and how do we actually work with these voltages and power and temperature and pressure values? What are the industries we apply this to, and why do we need these kind of precise measurement systems?
Yes, sir.
Okay, fine. So if you have any questions still here, we can take those questions. Okay, so now, Chinmoy, if you have some question, please.
Yes, sir. Sir, I'm getting confused. If a instrument cannot showing below resolution measuring value, then how could we know the instrument lead count?
Okay, so I think you joined late into the session.
Yes,
Uh,
sir. Yes,
I
sir. Yes, sir.
I will again go to the slide back and tell you. See, resolution and least count are approximately synonymous, but they are not exactly synonymous. Resolution means the minimum incremental value, as we have discussed till now. Least count is the minimum value that the instrument can read. So and again, I will give you one more example to understand the concept of least count. You all have seen vernier and screw gauges, right? So if I
Yes.
have a vernier scale, on my vernier scale, we have two scales. Fine. First is the main scale or the primary scale, and the other is the secondary or the augmented scale. Fine. Now, when we have to decide that what is the least count of this value, how do we calculate this as the minimum value of main scale minus the minimum value of the secondary scale? This is how we calculate the least count for these devices. And this is where the concept of least count is actually predominantly used. So I don't know if I have answered your question till now here, but there is a difference between the least count and the resolution. Least count is the minimum value that it actually reads, and least count is the minimum value that it actually reads, any system actually reads. And resolution is the minimum incremental value that can go up and down.
Okay. Okay, sir.
Okay, so I think I've made the point clear here. If any one of you have the doubt again, maybe you can go through the slides and we will discuss it in the next class again if you have some doubts here.
Okay,
Yes.
sir. Okay.
Okay, so in the previous example, we took a deflection type gauge where we were saying that it is a speedometer kind of a thing, or a galvanometer to be precise. And then we took the example of a digital multimeter. Now, this is where we can classify our instruments. We can classify these devices in the types of instrument. One can be absolute devices and the other can be relative devices. Absolute devices are the one that make the indirect measurements, and the relative devices are the direct ones that take the measurements. Now, if we say what is indirect and direct in the last class as we did, now if I have to measure the force and I don't know what force exactly is at that point of time, what happens in the modern measurement systems is wherein we have the process control variable as a electrical parameter. And what are these electrical parameters? They are basically voltage and current. So what happens in today's instrumentation is we always get the answers in terms of the voltage and current. We always get the answers in terms of the voltage and current. Now, if I have to measure the force, I need to go through a process that is called as calibration. What does calibration means? Calibration means is we are getting the output of the sensor or the process control variable as an electrical quantity called voltage. Now this voltage needs to be converted into the force, or say pressure, or say temperature, any physical variable. All these physical variables always give the value in terms of the voltage. So how does it works? It works like you have I am talking in terms of these black boxes. We will go into depth when we will understand the concept of process control. Now, if there is a black box and there is a force that is being applied mechanically, say you are standing on a weighing machine. So what would this black box give as an output? It would always give as an output a voltage value V volts. Now our work is to measure this force, and we are getting the output in terms of the voltages. So this is the process that we apply here called calibration, and we get the answers in terms of the force. So what we do, we say that force here is a function of the voltage V, or the temperature here is a function of the voltage V, or the pressure here is the function of voltage V. And when I say V and I, we will consider to be analogous. Fine. So calibration means finding this function. There is a mathematical value to this function, and based on this we find the values of forces at different values of the voltage over the time. Time is a very essential period when we are understanding the physical signals. Is this understood here?
Yes.
Okay. So having talked about this, now let us classify our devices into analog devices and digital devices. So what are analog values? If anyone can tell me, what are analog devices or what are analog signals, if you know?
which pointer has which has pointer.
Okay, that has a pointer. Anybody else? If you have some answers?
Maybe they're deflection type.
Okay, the deflection type. Okay, so first let us understand this word analog, and then we will come to digital, and then let's see how does this value actually apply to the instrumentation systems or the instruments. So as many of you have told, this can be the example for a analog device. Now, why does this is being called as analog? So let's first understand there are two kinds of things. One is a continuous time system, and the other is the discrete time system. Now, when my system here is reading the values of this scale from here to here, what it is doing is it is moving continuous in a continuous fashion over a linear scale. Right now this is a linear scale. It can be a non-linear or a logarithmic scale also, but we don't have devices that are non-linear in nature in terms of the instruments that we are discussing right now. Fine. So these analog devices or the analog systems or the analog instruments give us the value continuous fashion, as we have discussed here, as compared to what? As compared to time. So if I say I have a graph here of time, I will get some curve like this. Whatever this value is representing, if it is representing speed or time or speed or voltage or pressure or whatever it is representing, we are calling this as variable V. So over the period of time, it gives us continuous values. Okay, so if it is, say, 1 here, and it is 2 here, and it is 3 here, and it is 4 here, and it is 5 here, so it moves from 1 to 2, 2 to 3, 3 to 4, and this kind of a device is called as an analog device, analog measurement system. So the two basic common types of system, as you said also, are the deflection type instruments, and the other is the null type instruments. So deflection type and null type go with the same approach to measure the values, but they represent the values in absolutely different fashion, absolutely out of phase fashion. Like how? Like if this is my device and it is reading some values, and based on the values it is giving me a deflection, this is called as a deflection type instrument. What will happen in a null type instrument? In the null type instrument, it will give you the maximum value at some point of time, and from the maximum value, whatever value is being applied to it, it will start in a negation fashion and say if the full scale for this device fs is 180, and we consider this to be 0 to 180. Let us say that this is a protractor kind of a thing, and these values are giving us angles. So the full scale goes from 0 to 180. Now, if it is a deflection type instrument and it gives you a value, you are reading a value of 30 degree, what will happen is you will go from here to here. But in a null kind of a device, what it does is it will initially show you the value to be 180 degree, and it will start moving in the reverse fashion. So if you are reading 30 degree, it will give you some value to be 150, and it is actually the difference between 180 and 50 that is the answer for you. So these are our analog devices or analog systems. Now let us move and see what exactly is the digital instruments. The digital instruments, to be understood in a very basic or very common fashion, can be it gives us values in the form of this. It can be a number that is represented in the number scale that we read. So it gives us a direct readout. We don't have to measure the uh, scale, and it does it automatically for us. Now, to do that, there is again what we called as a black box there at the back end of the device, and there is again an analog system that is actually reading the values and giving it, and that analog system is being passing through the black box, and it is giving us the digital values. Now we don't need to go into the detail of this black box, but for your information, this is called as an analog to digital converter, that is itself a class of circuits that is being taught to the people who study circuits. So it gives us a value like this. So the most common type of devices that we go through these days are the digital multimeters, the speedometers in the new cars that you see come up with these digital scales wherein you see the value to be 120 kilometers per hour or 110 kilometers per hour or 60 kilometers per hour. So they give you these speed values directly as representing as speeds. Then we have digital thermometers. So instead of you going onto the mercury scale and measuring what is the temperature, these digital thermometers give you values directly as say as 100.9 degree Fahrenheit. Is this clear till here?
Yes, sir.
Okay. So if this is clear, let us okay. So let us move on and do a few numerical problems here at this stage. So let us say we have a weighing machine and we want to measure the weight of apples that we have, and we are putting the apples here onto this basket that is in turn kept on the weighing machine. Now let us suppose the absolute weight of the apples was 10.65 kgs. My weighing machine measured a value and the measured weight it showed was 11 kgs. I want you all to solve this problem and tell me what is the absolute error in the calculation, the relative error in the calculation, the percentage error in the calculation. These three values I want all of you to find out. I'm giving you 5 minutes to solve this problem. It should not take a lot of time.
Absolute error is 0.35.
Okay.
The relative value is 0.35 divided by 10.65.
So 3.28% error.
Okay, rest. Manoj and Mukul, have you solved the question? Adarsh?
Yes, sir. I also done. I also did it. The 2.8% percentage of error.
Mukul, Manoj,
3 point.
Mukul, Manoj, and Adarsh, did you solve?
Sir,
Yes,
3.6.
3.28 is the relative error.
Okay, so
Absolute error is 0.35.
okay, okay. So I think most of you have got the problem. So the absolute error is the measured weight minus the absolute weight. The relative error is measured weight minus the absolute weight by the absolute weight. And the percentage error is the measured weight minus absolute weight divided by absolute weight into 100. So this problem is understood, and if we get questions related to errors, we can always solve these in the fashion we have discussed. Now let us see a few problems on the resolution that we have discussed today. Okay, so say the device is used, we have a digital thermometer. So this digital thermometer is used to measure the temperature of a human body. Now, the resolution of this device is 0.04 degree Fahrenheit. Fine. The temperature of the body that is being measured is, say, 100.1 degree Fahrenheit. I want you to calculate the error due to the resolution in this value. Have you understood the question? Have you understood the question? Is there a doubt in the question to anyone?
Sir, could you repeat again
Okay.
the question?
Okay. So my question is, we are using a thermometer. The resolution of my thermometer is 0.04 degree Fahrenheit. The value that I am measuring right now is 100.1 degree Fahrenheit. What is the possible error in the value that we are measuring right now?
0.02.
Uh, 0.02 is the error,
No,
and
this is more of a concept based question. You need to think on the problem. Is there a error first of all? Is there a possibility of error? And if there is a possibility of error, what is that error? I want you to think on this question. We will have a
uh,
discussion on this.
the true value exactly, I guess 100.08 Fahrenheit, and it will show the 100.1 Fahrenheit.
It may be 100.08 or 100.12. So always there is a possibility of 0.02 error. I think so.
Okay. Rest of you? Sahil, have you understood the problem?
Yes, sir.
Did you get the answer?
Actually, no.
Okay, okay, okay. So let us look into what can be the error. So we are saying the measured value right now that we are measuring is 100.1 degree Fahrenheit. Now, the resolution that my device is giving is 0.04. So what will happen is whatever values will increase will always increase in the multiples of 0.04. This x is a number. Fine. So after 0.04, that is 0.04 into 1, we will have 0.04 into 2, and then we will have 0.04 into 3. So 0.04 into 2 accounts to 0.08, and 0.04 into 3 accounts to 0.12. Now, if we have read accurately till 100, our next value can be 0.04, it can be 100.08, it can be 100.12. Fine. Now, if my value that it can read is, I only have a one decimal place and it is giving as 100.1, there is a high possibility that we could have either this value or this value. So 0.08 it had approximated to be 100.1, or 100.1 it had approximated to be 100.1. So there is always a possibility that we will have in this situation, in a situation like this, wherein the readout is 100.1, we have the error of 0.02. So that can be 0.1 minus 0.08, and also it can be 0.1 minus 0.12. So in either case we can have a plus 0.02 error, or we can have a minus 0.02 error. Have you understood the concept of resolution here?
So in this case, if the error is 0.04, my point is plus 0.02 to minus 0.02. Is
No,
this
no,
the error or error is
no, no,
0.02?
no, 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 no. See, this is a possibility that we are discussing. It could have been 100.08 also, that it is reading as 100.1, and it could have been 100.12 also, that it is reading as 100.1. We would not know from this device that it was actually 100.12 or 100.08.
Sir, what if it is showing 100.04?
If it is showing 100.04 and we have a resolution that can go, I mean the device that can read two decimal places, then it should be perfect. There should not be a error. If we have a device that can read the value to be 100.04, and we have a resolution, we know that it is 100.04, in this condition it should be a perfect value wherein absolute value is equal to the measured value. But sticking on to the problem that we were dealing, there is no range of absolute error that we can find out in this problem. Whoever was asking this question and saying that from minus 0.02 to 0.02, we will have a 0.04 error. No, this is not the case. We will have an absolute error of either 0.02 plus or minus 0.02, but there is not this range of errors that we can calculate here.
So that is this is the maximum amount of error can be identified from this. The
Yeah,
maximum amount of error.
so the maximum amount of error in this case is 0.02. So if this is my base value, it can be plus 0.02 or minus 0.02, but it will always be this absolute error. There is not, we cannot calculate a range and say that the actual error is 0.04. No, this is not how we calculate it. We can say that the maximum error can be 0.02 either in the plus direction or in the minus direction. And this is how we actually write the errors. This is how the specifications are given as plus minus error. So we will always say that we have a plus minus 0.02 error. We always write the error in the form of plus minus. We do not give this as adding these two errors. Is this clear?
Yes, sir.
Manoj, yeah, you were having a doubt in this. Is this clear? Okay. So let's move on to the next question and see one more question of this type. We have a deflecting type instrument and our range is 0 to 112. So my full scale here is FSD, full scale deflection is 112 units. It can be anything. Now this is distributed over four uniform divisions. And seven uniform subdivisions. So my scale is 1, 2, 3 and 4 here. This is one section, this is the second section, this is the third section, and this is the fourth section. And each section here is made up of 7 subdivisions. Now I want you to find the least count of this device. Then if the measured value of this device is 86, then you have to find, is there some error in the value. Have you understood the question?
Yes.
Okay. Okay. So let us solve this problem.
List count is 4. I think so. List count is 4. And there must be error of 2 units. Am I
Excellent.
audible?
Yes, yes, you're audible, but I want others also to solve this and then we will go
Okay,
for
okay,
the
okay,
second
okay,
part.
okay. Okay, okay.
So all of you have solved this?
Yes, sir.
Sahil, Mukul, Adarsh, have you solved it?
Yes, sir.
Yes, sir.
Okay. So what is the answer that you got for least count?
Sir, 4.
4.
The four in each.
And what is the error if it is reading 86?
Sir, plus
2.
minus 2.
Two.
Plus minus
2.
2.
Yes, sir.
Okay, so I think this has made you very well understand the concepts. So the thing was we were reading from 0 to 112, and if we divided it into four uniform divisions and seven subdivisions, so it was actually 28 subdivisions that were being made. So the least value of this was 4. So our least count becomes to be 4. After 0 it would only read 4. There cannot be something here as 2 or 3 or 1. So for 1 it will give the value to be 0, for 3 it will give the value to be 4. To be very precise, near to be, if the value is 2, it should be either 0 or 4. So there is always the possibility of this plus minus 2 error. Understood, all of you?
Yes, sir.
Okay. Now let us go on to understand the applications of the measurement systems. Now see, there is a very striking difference between how we are going ahead with this course, how measurement systems have evolved, and how metrology, say if it was taught 30-40 years ago, and how metrology being taught today, there is a very striking difference. And why is that difference? Because see, uh, if you have to measure a length L, the most common device that you know is a scale. If it is very scientific length that you measure, you would go with something called as a vernier. If there is a diameter or thickness, for that thickness we would rather go with something called as a screw gauge, and so on and so forth. So these were all what? Mechanical instruments and mechanical manual instruments. We had to operate them and we had to read the values of our own, and it was mostly analog readouts, and there were always errors, human error, device error, application error, and so on. Now we are moving towards automation in almost all the sectors of the industry, and everything is being controlled using computer operated programs. So now when we study metrology, it becomes important to us to understand what is this process control system or process control method or procedure. So the first application wherein the measurement systems are used or are very predominant is this process control system. So how does it works is, see, to understand a plant, we have to understand that there are variables involved in a plant. Now, what are variables? We all know that there are two kinds of signal. One is the variable and the other is the constant. Now, constant, once known, is fixed. It will not change its value. So we can have a system wherein we are putting a weight of a block on a plastic sheet. Sorry. So we can a weight of a block on a plastic sheet, and once measured, it remains constant. So what we can do is we can just put a weighing balance here, measure that force and conclude that okay, this is say x kgs of force being put on my block, and this is done. But say there is an interconnected system that we are operating on, and we have a device or a system or a process, whatever you want to understand, that regulates the speed of an engine. So what is my output of this system is the speed of the engine. The rotor precisely. Now I want this rotor of mine to rotate at a speed of say 10 meters per second, or if it is a rotary motion, to be very clear on the concepts, let us say 10 revolutions per second rather than going per meter per second. Let's say it is 10 revolutions per second. This is the speed of the engine that I want. Okay, now if this is the speed of the engine that I want, and how is this speed being derived comes here as the fuel being inserted. Okay, now this fuel in turn is being driven from a pipeline that has a fixed temperature and pressure and volume. Okay, so the fuel is being inserted into the engine from this pipeline that has a temperature, pressure, volume. Based on the insertion of the fuel, the amount or the volume of fuel that is going to the engine, the speed of the engine is being derived here. So if I want to break down this entire system, I can always write a process block as a plant. It has a input, it has a output. Okay, so this is a open loop system wherein we are putting the input and we are getting the output. So say if we calculated that at an injection of 0.5 ml of fuel per second, we will get a speed of 10 revolutions per second. We have a very high efficiency fuel based on which we are getting this output. But this 0.5 ml per second is not constant. This is being in turn controlled by the temperature and the pressure. Now say when we did this in the previous slide and we said that this is coming through a pipe. Now if I am saying that this is the pipe through which the fuel is coming out, I have already fixed the volume of this pipe. The volume of this pipe is not going to change. We also say that the pressure is also somewhat kept constant and it won't change. But because it was kept in open and it was a hot summer day, so the temperature T, it started rising. Now, because this temperature T started rising and we know that the flow of the fuel we have decided was a function of the pressure, volume and the temperature, and these two being constant but this increasing, the flow started to increase. So now we are not having this flow of 0.5 ml per second, but it increased to say 1 ml per second because of the rise in the temperature. Now because this 1 ml per second rise is there, we got, and we have said that with the insertion of the fuel, the output or the speed of the rotation would always increase. So with this 1 ml per second, the revolution increased to be 15 revolutions per second. And this is not what we wanted. So there is an error generated, and this error has to be informed at the input so that the input can be reduced again. So there comes in a feedback loop from the output to the input, and we start to reduce this value from 15 to 10, and for doing that we have to reduce the speed by 0.5 ml per second. So this is a basic example of an instrumentation system wherein automated instrumentation works, and we have sensors and devices that gives us different values, and already we have decided that This is how we calculate the errors, and based on these errors, we begin to operate our plants with the desired capabilities. Do you have any questions on this discussion? Does anybody has any question on this?
No, sir.
Is this understood clearly? The operation of a plant?
Yes, I got it.
Yes.
Okay, so if this is understood, then we will close our session today here, and we shall meet next Saturday with the new topics that will be taught to you in in this week's lectures. I request all of you to please be ready with some of the problems, because these are actually problem solving sessions. So if you come up with the problems that you have solved and you're not able to solve it, then we can get a more practical and numerical approach to this course, and it would be beneficial for you. So I'm writing down my
Can you
uh,
get these videos, please? Last video of the last week and this week of these the discussion sessions.
sorry, I could not hear you.
Sir,
Video of the discussion sessions.
Yeah, so I think the videos are being uploaded on YouTube. So you can go on to the channel Abhinav Sharma PMRF, and you will find the YouTube lectures. So just wait a second, I'll give you the link here only.
Okay.
So today's lecture will also be uploaded on this link, so you can just go through this. Okay, fine. So we will close for today's session, and then we will meet next Saturday this time.
Okay, sir. Thank you.
Okay.